Go into the next topic with respective to the second module, which is pertaining with scaling and small geometry effects and along with MOSFET capacitances. So the purpose of this particular topic is we need to shrink the size of the IC. When you're shrinking the size, you have to have a different dimension. So the dimension exists as it is, but you have to scale it. You have to have a parameter which has to be scaled. Normally we write the scale on the graph. So 1 centimeter is equal to 10 volts or 1 centimeter is equal to 1 meter. But that doesn't represent that it is 1 meter. Then when you go back and scale up, you do the reverse procedure. If you have 5 blocks on your graph, it is nothing but 5 meters, because one block represents 1 meter. So this is how the scaling helps us, and we are all quite familiar by now, I hope. So we'll look into this topic now. So the next topic is the transient response. Generally, the transient response is the one which is taken with respective to the AC response. In DC analysis, V out is got if V in is constant. But whenever we consider in an AC response, it is fluctuating, it is changing, it is sinusoidal. So transient analysis, V out is got only if V in changes, and therefore it requires to solve or to go ahead with differential equations. Now we consider a step or a ramp response, that is considered as the input starting from 0 and trying to achieve to the logic 1. So or to from 0 to 1 logic, or from 0 to VDD volts. That would be your rise time, and from VDD to 0 would be the vice versa, which is the fall time. The fundamental way to compute delay is to develop a physical model of the circuit, write the differential equation describing the output voltage as a function of input and time, and solve. So this is how we calculated the delay, all the while using differential equations. And the solution of the differential equation is called as the transient response. And the delay is the time when the output reaches half of it, that is VDD by 2 or 50%. So the differential equation is based on the charging and the discharging of the capacitances in the circuit. As we all know, the delay is calculated by the constant R and C. So the capacitance plays a prominent role in finding out the differential equation, which is based on the charging and the discharging. Therefore, the circuit takes time to switch between the capacitance. The circuit takes time to switch because instantly capacitance cannot charge. Therefore, it will take little delay, or that charging is normally given as a small arc. Therefore, we need to see to it that has to be overtaken, and therefore the capacitance has to be charged with the current, and then the voltage on the capacitor varies with respect to the formula given here, as the current is dependent on C and dV by dt. So the differential voltage between the two nodes will be considered, along with the capacitance will give the current flowing in that particular node. So every circuit has some capacitance, which has already been told, because our MOS is a layered structure. Every layer there is a resistance and a capacitance. In between two layers there may be capacitances. So in an IC, it consists of gate capacitance of the load and diffusion capacitance of the driver. So as I have told, you have two stages. So this is your one part of the circuit, one inverter which acts as an input, and this acts as another input which acts as a load. So this can also be, input can also be called as a driver. Driver drives the load. Therefore, this is the case. But right now we are talking in terms of gate capacitance. So gate capacitance of the load has to be taken. Gate capacitance of the load is somewhere here near the gate terminal, and the diffusion capacitance is at the drain. So the transistor current depends on the input and the output voltages. Yes, just now we have seen the transistor current depends on the input gate and the output voltages. To illustrate these points, consider computing the step response of an inverter. So we have an inverter, and to the inverter we have given a step input or the step response. So figure A shows an inverter X1 driving another inverter X2 at the end of the wire. So this is a wire which also has its own capacitance and resistance. Suppose a voltage step from 0 to VDD is applied at node A. So here at node A, we are in the rising edge. So rising edge is 0 to VDD. Still we are in 0. So when it is applied, we wish to compute the propagation delay through x1. That is, what is the delay from the input step until the node B. So we need to find out what is the delay at node B, because till it crosses VDD by 2. So this is what is our understanding, and how do we proceed further? We will look into the next slide. So this is how the representation of a diagram looks. So here the capacitances has been shown. When you have a transistor, there are three terminals. One is the gate, one is the source, and the other one is the drain. Similarly, in N-type, you have the drain, you have the source, you have the gate. So these are the capacitances annotated. Now we have something called as diffusion capacitances. So source and drain are nothing but at the diffusion layer. The capacitances at the source and the drain are called as diffusion capacitances, and since it is with respective to source, it is suffixed as Cs, and B is the diffusion or the substrate body. P1 is the type of the transistor name we have given. Similarly, we have DP-CD, drain P1, source at the NMOS it is N1, and it is at the source, drain, and here the second one at the bottom is your source, so it is suffixed like this. It is suffixed. So whenever we have the driver, you shouldn't consider the gate capacitances. Instead, you should consider only the drain and the source capacitances. That is what is in other words called as diffusion capacitances. And obviously the wire has its own capacitance. Now we are talking about the load. So this is the load. So only at the load always please consider the gate capacitances. So gate capacitance, as I have already shown, this is nothing but an input of a inverter. So you have PMOS on the top and NMOS in the bottom. So therefore you have gate capacitance of PMOS P2, gate capacitance of NMOS N2. So the gate capacitances are considered at the load and diffusion capacitances are considered at the driver. So there are diffusion capacitances between the drain and the body of each transistor, and between the source and body of each transistor, CDB and CSB. B here is called as the body. The source to body capacitances have terminals tied to constant voltages, and that's they do not contribute any switching. And one more thing, please notice or please observe, in the PMOS, whatever the capacitances we have, they are connected to VDD because this is the pull-up network. Whereas in your NMOS, they are connected to ground because they are pull-down network. So it is also irrelevant whether the second terminal of each capacitor connects to ground or both or power, because both are constant supplies. So for the sake of simplicity, we can draw all of the capacitors as if they are connected to ground in the NMOS, and in the PMOS they are connected to the supply. So this is how capacitances are connected. Next we have a simplified and an equivalent circuit. So figure C shows the equivalent circuit diagram where all the capacitances are lumped into a single Cout. So all have been considered as a single capacitance. Therefore, you have to add the diffusion capacitances. That is, one drain capacitance of PMOS, one source capacitance of PMOS, one source capacitance of NMOS, and one drain capacitance of NMOS. So CD N1, CD P1, C wire, and source capacitance of N2, source capacitance of P2. So all these are added and we call it as Cout, inclusive of the wire capacitance. So this is the simplified diagram of the inverter which was being considered in the previous example, or in other words we can call it as an equivalent circuit. Now before the voltage step is applied, A is equal to 0. When A is equal to 0, N1 is off. So only the PMOS transistor is working. 0, complement 1, therefore P1 is on and this is off. N1 is off. So what is the voltage at VDD? What is the voltage at B? Since this is off, whatever is the VDD, it has no path to go to the ground. Therefore, all the voltage or VDD is concentrated at this node, and this node is nothing but VB. Therefore, the voltage here is VDD. The voltage at B is VDD. And after step, you have the input falling. So, when the input is 1, when the input is 1, 0, so PMOS is off and N1 is on. So when N1 is on, what happens? Since this is an open circuit, you have no path for the VDD to flow here. So whatever is the voltage available, that will eventually get discharged, and whatever the voltage here B drops to 0. And at the same time, when the voltage here is high, when the voltage at node B is high, C is charged to the maximum. C is charged to VDD. When this is an open circuit and N1 is on, C has a path to discharge. So C has a path to discharge like this. Therefore, C discharges through this path, and the moment it is discharging, the voltage here happens to be 0. So the rate of change of the voltage VB at node B depends on the output capacitance and the output current through N1. Therefore, in other words, our output current is, since it is flowing like this, it is negative, and C out, whatever your current is dependent on C out dVB by dt, and since it is in the reverse direction, we have it as minus IDSN, since it is NMOS. So this is how the current expression is given in terms of a simple inverter. So once we have analyzed the circuit, we will look at the respective current expressions in the transient response. If the gate is at VDD, that is when the gate is connected to 1 and the source is at 0, the drain potential would be VB. Therefore, VGS can be substituted as VD and VDS can be substituted as VB. And since N1 is in saturation, VB falls below VDD minus VT, and therefore N1 enters linear region. So by rearranging and using the differential expressions governing VB, we get the expression like this. During saturation, the current is constant and VB drops linearly until it reaches VDD minus VT. Therefore, the response is computed numerically, and the rising output response is computed in an analogous fashion and is symmetric with the falling response. So in this case, if beta P is equal to beta N, then the rising output response would be the same as that of falling response, only if the aspect ratio is equal. So this is with respect to the responses. Next, we have seen that calculating in terms of differential equation is little time consuming. Therefore, we go to the representation of RC delay model. So delay can be calculated using RC model. And what exactly happens in RC model is it approximates the nonlinear transistor IV and CV characteristics with an average resistance and capacitance. So the average value of the resistance and capacitance is considered, and the RC delay model can be approximated. And along with this, after you find out the RC model, we need to calculate the effective resistance. So what exactly you mean by effective resistance in terms of RC delay model? The RC delay model will assume the switch transistor here is replaced as a switch along with a resistor in series. In RC delay model, transistor or the CMOS, PMOS or the NMOS transistor is replaced with a switch along with a series resistor, and therefore the effective resistance is the ratio of VDS to IDS. The effective resistance, all of us know, R is equal to V by I, and the effective resistance is at drain terminal, therefore it is related in terms of VDS to IDS. A unit NMOS transistor is defined to have a effective resistance R. So an NMOS transistor will always have a unit effective transistor as R. And what about the PMOS transistor, unit PMOS transistor? PMOS unit PMOS transistor will have the resistance in the range of 2R to 3R, but normally we consider from this content as per the author will be in future using the unit PMOS unit PMOS resistance as 2R. How or for what reason the value of 2R is considered? If you look into this aspect ratio, the size of the unit transistor refers to a transistor with minimum length and minimum contacted diffusion width. So if you ever want to call a transistor as a unit transistor, it should have minimum length and minimum width. So the standard minimum width and minimum length is got if the dimensions are maintained as 4 by 2 lambda. So that in turn will give you 2:1 as the feature size, which is normally called as unit transistor size. Therefore, and one more thing, the R value of PMOS is more because of in terms of mobility. Because in mobility, what happens in PMOS, the width is normally made big because the mobility of holes is slow when you compare to electrons. Therefore, in order for them to move, if the space is very narrow, first of all the movement is slow and there is a lesser speed. Therefore, if you make the width wide enough, more number of holes can be drifted, and therefore the width is always twice that of NMOS. Therefore, the width of the PMOS transistor should be twice that of NMOS, and therefore when you say 2:1, PMOS is 2 and NMOS is 1. So throughout this book we will use 2R for examples to keep arithmetic simple, and R typically is in terms of 10 kilo ohms for a unit transistor. Next, we calculate the long channel model. Current decreases linearly with channel length and so resistance is proportional to L. Long channel, current decreases linearly with the channel length, so resistance. Therefore, the resistance of two transistors is the sum of the resistances of each transistor. And resistance of transistors in series is lower than the sum of the resistance because series transistors have smaller VDS. So resistance of two transistors in series is always the sum of the resistances, and resistance of transistors in series is lower than the sum of the resistances because series transistors is with respect to VDD. And similarly, the effect is more pronounced for NMOS transistors than PMOS transistor because of the higher mobility and greater degree of velocity saturation. So it is more prominent in NMOS than PMOS because NMOS has higher mobility and greater degree of velocity saturation. So what is the simplest approach is to neglect velocity saturation for hand calculations, but recognize that series transistors will be somewhat faster than predicted. Next, we need to understand gate and diffusion capacitance. Each transistor also has gate and diffusion capacitance. Every transistor has gate capacitance and diffusion capacitance. Normally, a transistor of K times unit width, if the width of the transistor is given or if the ratio is given, that is multiplied by the capacitance. Similarly, diffusion capacitance depends on the size of the source or the drain region. Wider transistors have proportionally greater diffusion capacitance. Increasing channel length increases gate capacitance proportionally. Okay. See, for a minimum, okay, when you consider it in 65 nanometer process, a unit transistor will have 0.1 micrometer wide and C is 0.1 femtofarads. Now we will understand, please concentrate on this. We will look into the equivalent RC circuits. So figure shows an equivalent RC circuit model for NMOS and PMOS transistors of width K with contacted diffusion on both source and drain. So this is the NMOS transistor and this is the PMOS transistor. So you have three terminals, gate, drain and source, and the width of both the transistors has been given to be K. So the PMOS transistor has approximately twice the resistance. As already told, R in PMOS is equal to 2R. R in PMOS is equal to 2R, whereas R in NMOS is equal to only R because of the width. because of the lower mobility. Then PMOS capacitors are shown with VDD as their second terminal because the N well is usually tied, and at the same time you can notice the PMOS capacitors are also connected. So if you look at this, every device has one capacitor at the gate, one capacitor at the source, one capacitor at the drain at the one capacitor at the source, one capacitor at the drain. Similarly, NMOS also, it has gate capacitance, it has drain capacitance, and it has source capacitance. Now when it is with respective to resistance, so resistance will be divided by K, that means the resistance decreases. So whenever you have the width given here with respective to a NMOS or a PMOS transistor, the resistance decreases, and that decrease is shown by R by K, and the capacitance is multiplied by that factor which is given as Kc. So if you notice, all the capacitances are multiplied by K, whereas all the resistances are divided by K. And since already proved, the NMOS has R ohms, so R divided by K. So this is with respective to NMOS. If you look at with respective to PMOS, the resistance of the PMOS is 2R. So 2R is the PMOS resistance, and the resistances and the capacitances are Kc only as shown, and it has to be divided by K, so it is divided by K. This is what are the equivalent RC components replaced here with respective to a transistor as a switch. And one more thing you have to notice, in PMOS all the capacitances are connected to VDD. All the capacitances are connected to VDD, and in NMOS all the capacitances are connected to ground. So the same circuit is shown here as an example with 2 1 and 2 1 here as the width, and if you just consider this, we will have the representation. So this is the equivalent circuit. How did we derive into this kind of a circuit? So as I told you, gate capacitances are connected here, therefore you have gate capacitance here as well as here. Okay, let me show you. You will have gate capacitance connected here and here as well. So since the K value here is 2, the gate capacitance will be 2C and 2C. Next, source also has one capacitance. Since the respective PMOS width is 2, it will be 2C. Since the diffusion is also a capacitance, it will also be multiplied by 2, and it is 2C. So this is with respective to the first stage. So first stage. Similarly, the ratio of NMOS is 1. Therefore, R is 1. R is 1. Here R is 2R capacitance. So this in turn is nothing but 2R by R. Therefore, the value of R happens to be 2R by 2. 2R by 2. Therefore, the value of R for the PMOS happens to be R. Whereas here the value of the R is R by 1. Therefore, it is R. And capacitance, since it is 1, it will be C into 1 at the drain as well as at the source. So all are pulled down to the ground terminal. This is pulled down to the supply terminal. This is with respect to the first stage of the inverter, which is nothing but the driver. Next, we have the next device, which is the load. So which is the load, which is given here with 2 and 1. So when you again replace this, you have the resistances and capacitances, but for the load we will be considering only the output capacitance. So output capacitance is given by C, 2C and C. And the equivalent circuit of this, since this is connected to VDD, this is connected to ground, they have their roles very less in terms of charging, therefore this can be redundant. Now how many capacitances you have? 2C, diffusion capacitances are 2C, 4, 5 and 6. So the diffusion capacitance is equivalently written as 6C, and what is the R value? R value is R. Only one device is on at a time. Since this is an open circuit, this will have low contribution or zero contribution. Therefore, only R is considered. Therefore, this becomes the equivalent circuit for an inverter. So that so 6C is got by 2C plus 2C4 and 5C. So this is how we consider. Shows an equivalent circuit of the first inverter driving the second inverter's gate. If the input A rises, the PMOS transistor will be on and NMOS is on and PMOS is off. So this shows the two capacitors and the total capacitance is given as 6C. So this is with respective to the simple inverter and its equivalent inverter.